to give a talk, Dmitriy Bilyk from University of Minnesota. He is an expert in minimum energy problems and actually, very active in this area. Published many papers, interesting papers, and the second talk related to Stolarsky invariance principle.
Yeah. So thank you very much, Oleg. So thanks for the invitation. Yes, and I'm very happy that Peter Boyavlenkov already mentioned the Stolarsky invariance principle in his talk. So I will talk about this interesting principle which connects energy and discrepancy, and the talk will be fairly elementary. This has been a very popular topic recently. I will not have time to talk about all possible generalizations and variants of this principle, but I will tell you a little bit, and I will tell you about some fairly easy forms, but which have immediate applications to some problems in discrete geometry. So let me start. As I said, everything will be quite elementary. So I'll start by introducing the main players. You've already seen in a couple talks, at least you've seen the discrete energy. So here, for simplicity, I'll be doing things on the sphere. And right, so we have some function which depends just on the distance between the 2 points, but you could do it in an arbitrary domain, and the function could just be a function of 2 variables. And you're considering the discrete energy. And notice that for my purposes here, I normalize it. And if the function f is nice, if it's non-singular, then you can take all terms. If it's singular, you would usually have to exclude I and j, but in many examples, this will be a non-singular function. So if you're interested in regular questions, what are the minimizing configurations? Can you get something that maybe if you don't find the minimizers, which configurations are good? Can you get some lower bounds? And so on. So this is that you've seen these objects already. And probably one of the most famous problems of this type is the Thompson problem. About the potential that comes from the Coulomb law, and yeah, we all know that it's the exact answer is known only for a very small number of for a very small number of values of n, number of points. Okay, and Thompson problem, you can also generalize this to Rees S energies. You can consider other powers. Okay, and what will be interesting for us here is that you can also consider negative values of S, well, in which case you will have to maximize the energy rather than minimize. And when S is equal to -1, you get the sum of Euclidean distances. Okay. All right. And in that case, actually, you don't have any singularities, so things are good. Okay. So this is the basic setup for energy. In addition to the discrete energy, we will also consider the continuous energy, or the energy integral. Okay, and here is just the double integral of f with respect to a given probability measure mu. Here, and then the notation is chosen in such a way that it's very compatible. The energy integral with respect to this empirical measure, the discrete measure with equal masses, is exactly equal to the discrete energy as I defined it before. And it's quite clear that the two objects are very related. If you can get the answers for every value of n, you would also, by weak star density, get the answer for the energy integrals. If you know what happens with the energy integral, if you know the minimizing measure, you sort of know what happens when n goes to infinity, what happens to discrete energy when n goes to infinity, when the number of points is very, very large. And in particular, when we're in the sphere, one very important question about the continuous energy is whether sigma, the uniform surface measure in the sphere, is a minimizer. Because that would mean that in the discrete case, when you minimize the energy, as n becomes large, points become somehow uniformly distributed. So in that case, in that sense, you can consider discrete energy as some measure of uniformity of distribution, because, well, it's also clear heuristically, if you go back, for example, to the Thompson problem, that if you put electrons on the sphere, if you're looking for the equilibrium position, they're probably going to position them uniformly on the sphere, right? Somehow in an equidistributed way. Okay. Well, there is another way to measure equidistribution, and that's discrepancy. Okay, and here I will present the so-called spherical cap discrepancy. So you start with a collection of sets. So this will be the so-called spherical caps. So essentially what happens is you take the sphere, okay, and you cut it at some level in the direction of the vector x. You cut it with a hyperplane at level t. So this set here is the spherical cap. Okay, and then you have a discrete set of points on the sphere, and you just compare the empirical measure with the surface measure of this of the spherical cap, and you take the supremum, find the worst possible discrepancy over overall spherical caps. Okay. And in general, you can do it for other collections of sets if you choose a reasonable collection of sets instead of the spherical caps. You can also define a reasonable discrepancy. Well, but let's stick with the spherical caps for now. It's the most natural on the sphere, perhaps. Okay, it's clear that this also measures the extent of uniform distribution of equidistribution of this discrete set of points. Okay, so what's known about it? Well, if you take the minimum over all endpoint sets, you have almost tight lower and upper bounds. Both bounds are due to Beck, so it goes back to the 80s. You can see that there is this interesting difference between the lower and upper bounds of it's very little. It's a square root of log n. Nobody really knows if it should be there. It probably, and my conjecture is that it probably should be. So, and this square root of log usually comes from large deviation bounds. This upper bound is semi-probabilistic. It uses jittered sampling. But the suspicion is that this is probably the correct order of magnitude for this discrepancy. What you can do is you can take this supremum. Also, to make things a little bit simpler, you can replace the supremum by the average, as we always do, and in particular by the L2, by the quadratic average, and that leads to the quadratic discrepancy. Okay, so here, notice I take this expression and I take the quadratic average. I average over all centers of the spherical caps and over all heights of spherical caps. Okay. The average over all possible spherical caps. Okay, and in this case, that lower bound becomes tight. So this is also due to Beck. So here we know pretty much everything, at least asymptotically, about this discrepancy. And again, the upper bound is achieved by jittered sampling. So it's I won't go into details, but this is a semi-probabilistic construction. Basically, you take an equal area partition and choose a regular equal area partition and choose a random point in each part. Okay. Well, what is nice about the L2 discrepancy is that, well, there are several things. First of all, it opens the door to using Fourier analytic methods. Well, whenever you have L2, there's some form of Fourier analysis that comes into play. But even simpler, there are even simpler things that you can do. Since you have the L2, this L2 expression here, you can just square things out, multiply them out, and see what is going to happen. And in particular, what would happen here is that, well, you can replace this expression. You can just say, well, it's the sum of these characteristic functions. Okay, well, when you square out, you get pairwise products of such characteristic functions. Okay, so what does it really give you? So you will have two spherical caps, right, centered at two different points of your set. Okay, and then you integrate. So you get these characteristic functions, you integrate in X, well, you'll get the area of the intersection. And then you simply need to integrate that. It's not completely straightforward, but it's not terribly complicated computation. And that leads, this is one possible proof of the now famous Stolarsky invariance principle. Okay, so if you do the computation, you come up with this thing that the L2 spherical cap discrepancy plus the sum of Euclidean distances, this discrete energy, that's a constant. Okay, and that constant is equal to this continuous energy. Okay, so this is why it's called the invariance principle. So it says that this sum is invariant. Okay. This tells you a lot of things. This tells you that minimizing the discrepancy is exactly the same as maximizing the sum of distances. Okay. So you can also write it in this form. You can write it that the discrepancy is equal to the difference between the energy integral and this discrete energy. So this is sort of a cubature formula error. You can view this as the integral and this as the discrete approximation of the integral. Yeah, this has lots of immediate consequences. For example, you can see from this is probably one of the simplest ways to show, well, at least a simple way, an elementary way to show that this is all the discrete energy is always smaller than this continuous energy. Okay. So this was proved initially in the 70s by Stolarsky. His proof was a little, I would say, a little complicated. It was a little bit more general than what I'm stating here. And then there were at least a couple proofs given fairly recently, which are quite elementary. And so the proof that we gave with Feng Dai and Ryan Matsky is essentially the one that I described the heuristic of the proof. You just square things out and integrate and see what comes out from these overlaps between spherical caps. Okay. All right. Well, so you can see that we get the sum of distances. This is the Reese energy with S equal to -1, which I mentioned before. Okay, and so this was posed by Fejes-Tóth as a problem. So what are the minimizing configurations? And again, in this case, unfortunately, for very few values of n, the answer is known. But well, at least you know that you have an equivalent formulation of this problem. It's equivalent to minimizing the L2 spherical cap discrepancy. So as I mentioned in the beginning, there are numerous generalizations of this principle now. I will only mention some, and I will mention one very recent and very general form of this principle at the end of this talk. This was generalized to projective spaces and more generally two-point homogeneous spaces by Skriganov. This was also recently generalized by Alexander Barg to the discrete spaces and the Hamming cube, and this was mentioned in Peter Bavelenkov talk. Okay, and generally, most of the generalizations that you see somehow look this way. So you need to somehow connect an appropriate version of discrete energy and an appropriate version of L2 discrepancy. Okay, and extensions will have exactly this form. So either you'll have something that's very relevant in metric geometry, where you have the distance integral and the sum of distances, and you are comparing them, and that's equal to some form of L2 discrepancy. Or more generally, you can have some form of discrete energy and an energy integral. Okay. And you don't have to consider the L2 discrepancy for discrete sets. You can also do it for measures. So basically, if you go back to the definition, so here is the definition of discrepancy. Well, here, this is the empirical measure of the set of points Z, right? Well, you could replace it by, so this empirical measure of the spherical cap. Well, you can take an arbitrary measure mu and take the arbitrary measure mu of the spherical cap and then compare it and do the same thing. So you can do the spherical cap discrepancy for measures instead of sets of points. So, and that, yeah, that also would give you some sort of this Stolarsky invariance principle for measures. And that can be useful because if you can get something like this, that could give you information about what the optimal energy is, because then you know that the left-hand side is positive. So if you have some expression of this form, that would tell you immediately that that you know something about the optimal energy. Okay, so going in one direction is quite easy usually. So that's what I mentioned before. If you have a notion of discrepancy, then getting a distance integral or the energy integral, discrete energy, is easy. Just square things out and see what comes out, what sort of function you get. Going in the opposite direction is a little bit harder, although possible. And usually the answers that you get are a little more implicit. You get them in terms of the some orthogonal expansions and the coefficients of those orthogonal expansions. It's very hard usually to get explicit answers in this case, although you can sometimes. All right, so let me mention right away one application. So this application stems from another problem of Fejes-Tóth. It's about the sum of geodesic distances on this sphere. Okay, so Fejes-Tóth conjectured that if you take, so we're now replacing the Euclidean distance by the geodesic distance. So he conjectured that for even n, any centrally symmetric configuration should be a maximizer. And he solved it for some small values of n, but now this conjecture is completely solved. And one of the proofs in particular, probably I think the most complete proof, rests on a version of the Stolarsky invariance principle. And it's interesting that the Stolarsky principle itself goes back to the 70s, but this observation was made simultaneously. I think it was in the same months independently by us with Feng Dai and Ryan Matsky and by Maxim Skriganov, that if you replace the Euclidean distance with the geodesic distance, or rather, if you first replace the spherical cap discrepancy with the hemisphere discrepancy. So instead of taking all values of t, instead of taking all spherical caps, you only take spherical caps corresponding to t equal to 0. So that's the hemisphere. Then you get the same Stolarsky principle, well, but with a much nicer constant independent of the dimension and with the geodesic distance here instead of the Euclidean distance. Okay, and it's very easy to see. The argument is still the same, but what you have to observe is that the intersection, the area of the intersection of two hemispheres depends linearly on the geodesic distance or the angle between these two vectors. That's essentially all. Okay, well, the integral here is very easy to compute. That's the average angle between 2 points. The average angle is pi over 2. Okay. So this tells you then right away that this discrete sum is bounded by pi over 2. Okay. Also, it tells you that if it's equal to pi over 2, this hemisphere discrepancy should be 0. Okay. And it's quite easy to figure out when it is 0. It's 0 precisely when the point z is symmetric. Okay. Well, for example, one of the possibilities is that you have half of the points at one pole and half of the points in the other pole, and then almost every hyperplane, almost every hemisphere would give you discrepancy 0. Because almost every hemisphere will have exactly half of the points. And that happens with all symmetric sets also. It's a little bit more complicated when, the number of points is odd. Okay, in that case, essentially you have a you can characterize all minimizers still using the Stolarsky invariance principle. Basically what happens is that you have these symmetric sets, but then you can also have another part. You can have something that lives on the great circle and is a minimizer. It's not necessarily symmetric, but is a minimizer for the great circle. So this has this, you get additions, you get this little perturbations. You can have an addition in a great circle. This problem has a long history, so a lot of things were known before. So I think our proof here was the first for all dimensions with complete characterization of minimizers, both for odd n and even n. But yeah, we can't really claim that we solved this problem. A lot was known already, but it's a very interesting application of the Stolarsky, of a version of the Stolarsky invariance principle, I think. So I will mention one more. Okay. Before I move on, I'll talk briefly about what happens with measures here. So you can do the exact same thing with measures. Okay. So we had this. Let me move a couple slides back. So we had this Stolarsky invariance principle for discrete sets. Okay, well, again, you can do everything for measures instead of discrete sets. So then here you will just have the energy with this kernel for the given measure, and here you will have the discrepancy of a measure. Okay, so and here then, here's what the Stolarsky principle becomes. The proof is exactly the same. Okay, but then also you can look at this energy and you can try to understand what's, well, first of all, you get, so this is what I denote by I geodesic. Right, so this is this energy integral. So you see immediately that it's bounded by pi over 2. You can also prove that it is pi over 2, so the energy is maximized if and only if mu is symmetric. It seems almost obvious because this means that for sigma almost every x here, the measure of a hemisphere, so h of x here stands for a hemisphere in the direction of x, should be 1/2. And it seems almost obvious that that can only happen if the measure is symmetric, but it does require some proof, actually. It's interesting that it's not completely trivial to show it. Okay, but yeah, it holds. So all symmetric measures here maximize this energy integral. And that leads to an interesting dichotomy. If you consider this energy integral with different powers lambda here. So essentially it's an analog of Rees S energy for negative s, but with geodesic distance here. So you can say that this is geodesic distance Rees energy. Okay, so there is a phase transition at lambda equal to 1. Okay, so you can prove that for lambda between 0 and 1, you have a unique maximizer. You can also prove that for lambda greater, well, for lambda equal to 1, we just saw it. You have any symmetric measure is a maximizer. And when lambda is greater than 1, your maximizers collapse. Only measures which are concentrated at 2 opposite poles are maximizers. So you have a phase transition here at lambda equal to 1. And it's interesting to compare it with the original Rees energy, with the Euclidean distance. And this was done back in the 50s by Bjork. And there's also a similar phase transition, but it happens when lambda is equal to 2. Okay. So, and the behavior at the transition point is a little different. You have more maximizers here, so every barycentric measure works. So it's an interesting phenomenon, and I think it's an interesting general question. What would happen if you take an arbitrary compact metric space? I think that if you consider integrals of this type, I think the same behavior will persist, that there will be a phase transition such that after that phase transition, maximizers become discrete. So they collapse into just a few points. However, I don't have a general proof for that. So there are some other situations where we can prove similar things, but we don't have a general proof. So I think it's an interesting problem in general. And I'm trying to understand how the geometry of the metric space, how it will influence the phase transition, the power at which the phase transition happens. Okay, so I will mention one more problem by Fejes-Tóth. So this is the third problem of Fejes-Tóth already in this talk. So this is about the sum of acute angles. So essentially, well, okay, you can view your points on the sphere as you can take the lines generated by those points, and you can look at the angles between the lines. Okay, or you can say that you're going to the projective space, right? So essentially, instead of taking just the angle, the geodesic distance, you take either the minimum of the angle and pi minus the angle. So it's the acute angle between the two lines generated by these vectors. Okay. And now if you take the sum of these acute angles between lines, Fejes-Tóth conjecture that this is maximized by periodically repeated orthonormal basis, right? It's completely clear that if the number of points is less than the dimension, then you can take the orthonormal basis, and this will maximize this sum. But then what happens if the number of points is greater than a dimension? There are some partial results, but the answer is still not known. But the conjecture, which seems very reasonable, that you should just start repeating the orthonormal basis. For example, in R3, if you have 7 points, it will be E1, E2, E3, E1, E2, E3, E1. So that's the conjecture. The answer is not even known if the number of points is a multiple of the dimension. So if even in R3 for 9 points, the answer is not known, although it seems that it should be just 3 repeated copies of the orthonormal basis. There are some partial results in general, but the conjecture is solved on S1. And even there, it's fairly easy, but not completely trivial. And the reason I wanted to mention it is that there are several proofs known, and one of the proofs is actually a Stolarsky principle type proof. So on S1, if you consider the following sets, if you consider these quadrants, so take point X on the circle and consider 2 opposite quadrants in this way, for example. Okay, and then you can see easily that if you take 2 such sets corresponding to X and Y, then the intersection will depend precisely on the acute angle between X and Y. And then you can write out a Stolarsky principle for the discrepancy with respect to such sets. Okay. And that will give, you can use the Stolarsky principle to solve the conjecture on this one. That's just I think, acute application of Stolarsky invariance principle. Unfortunately, this doesn't give any information in higher dimensions because it doesn't seem to be possible to represent the acute angle in such a way. Okay, I have just a few minutes left, so I now want to briefly talk about some very recent results. So there is a very general version of the Stolarsky principle on compact spaces. So here, let omega be some compact space. And here, by the way, sorry, this is a typo. Okay. And let K be continuous, symmetric, and positive definite function in that space. Okay. Okay. And assume that mu is the equilibrium measure, the minimizing measure of the energy integral, IK, and assume that mu also has full support. Okay. Then you can find a function f, and you can construct a discrepancy, a notion of the L2 discrepancy, such that the difference between the optimal energy and the energy with respect to an arbitrary measure nu is equal to the discrepancy of that measure. So it's very general. So the way to think about it, for example, if you take f, if you're on the sphere and f is the indicator function of the spherical cap, you'll get the inner integral of the classical spherical cap discrepancy. Okay. So this shows that you can do it with more general functions, and it shows that you can always construct such a function. And the way to construct it, so actually this theorem, a similar theorem, first was obtained by myself, Ryan Matsky, and Feng Dai a couple of years ago, probably 18, on the sphere. And then constructing this function f, this went through the spherical harmonic expansions or Gegenbauer expansions. Here you need more general spectral decompositions, but it can be done. But this function f becomes fairly abstract, but we know that it exists. And a couple things that I wanted to mention is that generally it's not really so important here that I take the minimizer, that I know a priori that I'm taking the minimizer. So what it is important, the important property is that it's a so-called invariant measure. So let me briefly, so in the last, I'll spend 2 more minutes, I'll talk about invariant measures. So we say that a measure is invariant if its potential, that is, if we integrate k once with respect to that measure, if that is constant. Okay. So in particular, and that's all that you need. If you know that this property holds, then you can prove this theorem. You can prove this general version of the Stolarsky invariance principle for this measure mu. Okay, and we know that if you have, this is a basic fact from potential theory. If you have a minimizer, energy minimizer with full support, it will have this property. However, you can come up with various measures that are k invariant for different kernels. In particular, you know right away that if you're in a 2-point homogeneous space, or on the sphere, on the projective space, on the Hamming cube, and if your kernel is rotation invariant, then the uniform measure is going to be k invariant. So you don't need to know a priori that it's an energy minimizer. You just know that it's k invariant. There are other examples for. So let me mention one. If you take so if your omega is the interval -1 to 1, and k of xy is, well, it's again the Reese energy, essentially. It's x minus y, the absolute value. Then if you take the measure concentrated at 2 opposite points, this is actually going to be k invariant on omega. So there are cases when you have a k invariant measure not with full support. They arise, it's a very interesting topic, but I don't have time to talk about it. They arise in so-called rendezvous numbers. That's a very interesting topic in metric geometry. But let me mention a theorem that we're just finishing up a preprint about it. So we saw that positive definiteness plays a role here. So it turns out that positive definiteness, or conditional positive definiteness, well, or positive definiteness modulo a constant, well, in the energy, it doesn't matter if you're adding a constant. If there exists a k invariant measure with full support, then positive definiteness up to a constant is equivalent to a bunch of other properties. So the fact that k is positive definite is equivalent to the positive definite modulo a constant is equivalent to conditional positive definiteness. This is not true in general. And it's equivalent to the fact that mu is a minimizer of the energy in many different senses, that it's minimizer over probability measures, that it's also minimizer of over measures of total mass 1, but could be signed. This set is not even compact, which is interesting. So you don't get different minimizers in this situation. It's also equivalent to mu being a local minimizer, which is also interesting, which means that in this situation, you don't have any local minimizers which are not global. So, okay, I'll stop here. This is only a half of the theorem. It's also, there's this list of equivalences goes on, but yeah, I'll stop here. Yeah, thank you.
Okay, thank you very much. Very interesting talk and interesting review. Interesting area, actually. Questions? Oh. Okay. My question about how it is. What about uniformly distributed set of points? You know, it is in this discrepancy for if you have a sequence universal, and in this case, discrepancy of uniformly distributed sequence approaches 0, right?
Mm-hmm. Right. Yeah.
But it depends. It depends on measure, actually, right? And for regular, how from this point of view, is it? I assume that. Do you have some theorem? I mean, you considered several extensions.
Right. So okay. Right. So So if we go back. So let me go back to the definition of discrepancy.
Stolarsky principle, right? Because we
right.
have...
So right before. Right. So here you're comparing the. So you're comparing the empirical measure to the uniform measure, right?
Yeah.
And right, dependent on the notion of discrepancy that you take, and depending on the geometric situation, it may not be the right thing to do. So sigma may not be the uniform measure may not be the right measure, because again, let's go to the Stolarsky principle. here. So
Yeah.
so this tells you that for this notion of discrepancy, the corresponding energy is this. And we know, actually, you can check it. So you could check it. So it follows from this equality, but also you could check it in other ways, that this energy is maximized by the uniform measure. But if, for example, you come up with some other energy which is maximized by a different measure, okay, then where the optimal measure would not be sigma, then this discrepancy would not be very meaningful, right? Because, well, discrete, well, the optimal energy is not sigma. So that's what I meant when I said that energy integrals are quite important, even if you want to understand the discrete problems, because.
But no, this integral, I mean, in this particular case, we have 0, right? On the right side, I mean, asymptotically.
Well, on the right-hand side, no. Oh, you mean with the dimension?
No, it is right. I mean, the discrepancy has to be 0, right? Correct?
Well, the discrepancy goes to 0, right? And you know that the difference between this energy, discrete energy, and the continuous energy, yeah, it can go to 0,
okay,
right? And it can go to 0 precisely because this is your because this is your optimal, sort of your optimal measure. And you also know that this stays below this. This is less than the energy integral, and it. For uniformly distributed points, its asymptotically approaches 0 and then goes to infinity.
So you're not assume the discrepancy asymptotic for uniformly distributed. You not assume that it will be goes to 0. You assume or not assume? I mean, in your
this works for any set. So this essentially by definition, discrepancy
is 0. Yeah,
discrepancy goes to 0 and then goes to infinity. That's the definition of. You can take it as a definition of uniformity.
So you cannot consider it if you're not uniformly distributed. Okay.
Right. Yeah. But here, right, it tells you if it doesn't approach 0, that also tells you that this energy has to stay away from this from the optimal energy integral. Yeah.
Okay, thank you. More questions? Thank you.
Is it possible to quantify distance to uniformity if the discrepancies there is a given set, and we would like to know how far it is from the uniform in terms of some metric on the space of distributions, let's say Wasserstein distance to the, let's say, uniform measure?
Yeah, good question. Yeah.
Right. So I think, and I think there was some recent work by Steinerberger in particular. He actively, he was an active proponent of using Wasserstein distance.
Or any other distance, it doesn't matter.
Right. You can use various distances. So essentially, as long as you have some metric between the measures, you can use the distance between the measures as the quantification of equidistribution, right? And for some of these metrics, you can also prove either inequalities or sometimes even equalities for similar to the Stolarsky invariance principle, right? But yes, you can. So you can take the measure, whatever your measure mu is here. So it could be the empirical measure or some other measure, and you can take either some norm. You can also look at the total variation norm. You can look at the Wasserstein distance, and you can compare those, and that also gives you, right, of course, a certain measure of equidistribution.
Okay, thank you. We have a next. Yeah, thank you very much.